The deepest secrets of the cosmos often reveal themselves not in a blinding flash of insight or a grand planned expedition, but in the most unexpected of places, through the most mundane of means. Consider a quiet facility in Holmdel, New Jersey, in the year 1964. This was Bell Laboratories, a powerhouse of innovation, but one focused on the practicalities of human communication, not the vast, abstract mysteries of the universe. Here, two young American radio astronomers, Arno Penzias and Robert Wilson, were diligently working with a gargantuan piece of equipment known as the Holmdel Horn Antenna. This magnificent structure, shaped like a colossal gramophone horn, stood 60 feet long and 30 feet high, designed with a very specific purpose in mind: to facilitate satellite communication, particularly with the groundbreaking Echo 1 and Telstar satellites. Yet, as Penzias and Wilson meticulously calibrated their cutting-edge instrument, a persistent, vexing problem emerged. Their sensitive receivers picked up an inescapable, unwavering hiss. It was faint, uniform, and utterly baffling. This static was not localized. It emanated equally from every direction of the sky, regardless of where they pointed their massive antenna. It was a noise that stubbornly refused to be eliminated, clinging to their measurements like an unwanted shadow. They were telecom engineers, trained to optimize signals and eradicate interference, and this was the most obstinate interference they had ever encountered. Their quest to silence this enigmatic hiss became a year-long odyssey of frustration and meticulous troubleshooting. They checked every connection, recalibrated every dial, and painstakingly examined every component of their state-of-the-art equipment. Could it be terrestrial interference? They tested against nearby military radars and urban radio signals, but the hiss remained isotropic, coming from everywhere at once. Was it simply the antenna itself? Famously, their desperate search for a source of thermal interference led them to suspect the rather large population of pigeons that had taken up residence inside the horn. Convinced that the birds' droppings were somehow generating a thermal signal that skewed their data, they undertook the rather unglamorous task of cleaning out pounds of guano, even going so far as to install a makeshift bird deterrent system. Yet, despite their valiant, if somewhat comical efforts, the persistent, low-level background noise endured, unchanged. This was the psychological crucible of scientific discovery, the initial assumption that the problem lay with their instruments, with their own errors, rather than with a profound cosmic signal. It is a common human bias, a leaning towards the known, the manageable, the solvable within existing frameworks. They were battling a ghost in their machine, a phantom signal that defied all conventional explanations for instrumental error. But unbeknownst to them, just 40 miles away, at Princeton University, a brilliant physicist named Robert Dicke and his team, which included the equally brilliant theoretical physicist Peebles, were independently building their own radiometer. Dicke's team was driven by a theoretical prediction made decades earlier by George Gamow in the 1940s. Gamow had theorized that if the universe had begun with a hot, dense Big Bang, then a faint, residual glow, a relic radiation from that primordial inferno, should still permeate the cosmos today. They were actively searching for exactly what Penzias and Wilson were trying to get rid of. The pivotal moment arrived with a simple phone call. Penzias, still puzzled by their unwavering noise, learned of Dicke's work. The two teams connected, and the realization dawned with stunning clarity. The persistent isotropic hiss that Penzias and Wilson had so doggedly tried to eliminate was not an error, not pigeon droppings, not a fault in their antenna. It was the very signal Dickey's team was seeking, the cosmic microwave background. This accidental discovery, born out of frustration and the meticulous pursuit of unwanted static, transformed a mundane engineering problem into humanity's first precise measurement of the universe's primordial glow, earning Penzias and Wilson the 1978 Nobel Prize. It was the first time we had truly peered into the emptiness of space and found it not to be empty at all, but filled with the faint thermal afterglow of creation. This revelation established a crucial precedent, hinting that this same emptiness might possess an even more mysterious, powerful property: energy itself. There is a common misconception that scientific progress is a relentless march forward, a pure pursuit of truth unburdened by human biases. But history, especially the history of cosmology, tells a far more dramatic tale. It is a story of fierce intellectual battles, of deeply held beliefs clashing with inconvenient evidence, and of the profound struggle even the greatest minds face when confronted with a universe that refuses to conform to their expectations. In the 1920s, as humanity grappled with the implications of the cosmic microwave background's faint glow, a deeper, more fundamental question loomed. What was the true nature of the cosmos itself? At the heart of this brewing conflict stood Albert Einstein, a man whose genius had already reshaped our understanding of space and time. By 1917, armed with his groundbreaking theory of general relativity, Einstein held a deep-seated conviction, rooted in both physics and philosophy, that the universe must be static, eternal, and unchanging. For him, the very elegance and order of the cosmos demanded this stability. Yet, when he applied his own equations to the universe as a whole, a disturbing truth emerged. His mathematics predicted a dynamic, unstable universe that would either expand or collapse under the relentless pull of gravity. This was an intolerable outcome for Einstein, a universe that wouldn't sit still. To force his perfectly crafted universe into a state of blissful immobility, Einstein introduced a new term into his field equations: the cosmological constant, represented by the Greek letter lambda. This constant acted as a kind of anti-gravitational force, a repulsive energy inherent to space itself, precisely counteracting the gravitational pull of all matter and thus maintaining a perfectly balanced, static cosmos. It was an elegant mathematical patch, an addition designed not from empirical observation, but from a profound philosophical bias, a necessary defense of a deeply held paradigm, rather than a mistake born of carelessness. For decades, this act was famously labeled his biggest blunder, a testament to how even the most brilliant minds can be swayed by their preconceived notions. But the universe, it turned out, cared little for human expectations. Even as Einstein was cementing his static vision, intellectual challengers were emerging, each chipping away at the foundation of his perfect universe. First came Alexander Friedmann, a brilliant yet tragically overlooked Russian mathematician. In 1922, working independently and purely through theoretical deduction, Friedmann derived the first solutions to Einstein's own equations that described a universe that was unmistakably dynamic, a universe that was either expanding or contracting. Einstein, upon reviewing Friedmann's work, initially dismissed it, asserting that it contained a mathematical error. Such was the strength of his conviction in a static cosmos that he overlooked the very implications of his own revolutionary work when interpreted by another. Simultaneously, across the continent, another visionary was at work, Georges Lemaitre, a Belgian priest and physicist. In 1927, Lemaitre independently arrived at the same conclusion as Friedmann regarding cosmic expansion. But Lemaitre went a crucial step further. He wasn't content with just mathematical derivation. He connected his theoretical findings to the sparse but growing astronomical observations of the time. Lemaitre boldly proposed that the universe was not only expanding, but had originated from an incredibly dense, hot state, a concept he termed the hypothesis of the primeval atom. This was the groundbreaking first iteration of what we now know as the Big Bang theory, a radical departure from the prevailing view of an eternal universe. The tension between theoretical prediction and observational evidence was reaching a breaking point. While Friedmann and Lemaitre had laid the mathematical and conceptual groundwork for an expanding universe, definitive proof remained elusive. That proof would come from the monumental work of Edwin Hubble, operating from the Mount Wilson Observatory high in the mountains of California. In 1929, using the observatory's 100-inch Hooker telescope, then the largest in the world, Hubble made his landmark observations of distant galaxies. He meticulously measured their distances and their recessional velocities, discovering that the further away a galaxy was, the faster it appeared to be moving away from us. This was the irrefutable observational evidence that the universe was indeed expanding, not remaining static. It was an expansion of space itself, carrying galaxies along for the ride like raisins in a rising loaf of bread. The evidence was overwhelming. Faced with Hubble's undeniable data, Albert Einstein finally conceded. He journeyed to Mount Wilson in 1931, visited Hubble, and reportedly acknowledged the expanding universe as a profound revelation. His cosmological constant, introduced to force a static universe, now seemed an unnecessary mathematical artifact. He famously called it the greatest mistake of his life, a regrettable fudge factor. What Einstein could not have known, however, was the cosmic irony that awaited. That discarded idea, the cosmological constant, would return a century later, not as a blunder, but as the most plausible, if still deeply mysterious, explanation for the universe's greatest enigma, the accelerating expansion driven by dark energy. In the cosmic tapestry, where distances stretch beyond human comprehension and time itself warps, a fundamental question once loomed. How do we truly measure the unfathomable expanse of the universe? For decades, scientists believed they had a grasp on its expansion, confidently predicting that the gravitational pull of all matter would inevitably slow it down, much like a ball thrown skyward eventually loses momentum. Yet, the 1990s would shatter this long-held conviction, revealing a truth far stranger, born from the meticulous observation of distant stellar explosions. This revolutionary shift in understanding began with a technological leap and the intense, often competitive spirit of scientific inquiry. Two rival teams embarked on an ambitious quest, the supernova Cosmology project, led by the American physicist Saul Perlmutter at Lawrence Berkeley National Laboratory, and the High-Z Supernova Search Team, co-led by the Australian astronomer Brian Schmidt and the American astronomer Adam Rees. Their shared objective was to measure the universe's deceleration, to precisely chart how quickly its expansion was slowing, providing critical clues to its ultimate fate. They just needed the right cosmic yardstick. Their chosen tool was a celestial marvel, the Type 1a supernova. These are not just any exploding stars, they are cosmic events of astonishing consistency. Think of them as universal standard light bulbs. When a white dwarf star, the dense remnant of a sun-like star, siphons matter from a companion star until it reaches a precise mass limit, roughly 1.4 times the mass of our own sun, it ignites in a thermonuclear detonation. This explosion always reaches a nearly identical peak brightness, making it an invaluable standard candle across the cosmos. By measuring how bright a Type 1a supernova appears from Earth, astronomers can calculate its exact distance. A fainter appearance means it is further away, a brighter one, closer. It is a deceptively simple principle applied to an incredibly complex phenomenon. The challenge of finding these fleeting cosmic beacons was monumental. These were not events occurring every night. They were rare, occurring in any given galaxy only about once every several centuries. To find them, the teams first needed cutting-edge digital imaging technology. This meant the widespread adoption and refinement of charge-coupled devices, or CCDs, essentially the predecessors to the digital cameras in our phones, but orders of magnitude more sensitive and precise. These revolutionary detectors could capture the incredibly faint light from galaxies billions of light-years away, allowing astronomers to see deeper into the past than ever before. But the technology was only half the battle. Securing precious time on the world's most powerful telescopes, giants like the Hubble Space Telescope orbiting above Earth, or massive ground-based observatories such as the Keck telescopes on Mauna Kea in Hawaii, with their mirror diameters reaching 10 meters, was fiercely competitive. Each team needed to scan vast swathes of the night sky, patiently hunting for tiny, pinprick flares that could signal a distant supernova. Once a candidate was spotted, rapid follow-up observations were critical to confirm its type and track its light curve, ensuring it truly was a Type 1a. This required complex computer algorithms, meticulously coded, to sift through petabytes of data, filtering out cosmic rays, satellite trails, and countless other celestial objects, all while identifying the signature fingerprint of a Type 1a supernova. It was an intellectual marathon, demanding incredible persistence and ingenuity from hundreds of scientists and engineers. The tension mounted through the late 1990s. Both teams, working independently, were systematically collecting their data, each expecting to confirm the reigning cosmological model, a universe expanding, but slowing down under the relentless grip of gravity. The expectation was clear. Distant supernovae, whose light had traveled for billions of years, should appear slightly brighter than they otherwise would, because the universe was expanding slower in the past. But as the data accumulated, an astonishing and deeply perplexing pattern emerged. The distant Type 1, a supernovae, were not brighter. They were, in fact, systematically fainter than predicted. This meant only one thing. Those supernovae were further away than they should have been. And if they were further away, it implied that the universe's expansion was not slowing down at all. On the contrary, it was speeding up. Imagine a car that you expect to be decelerating, but instead, you discover it is pushing the accelerator pedal to the floor. The initial reaction within both teams was not jubilation, but profound scientific shock and a wave of self-doubt. Could there be an error in their instruments? Was there a flaw in their understanding of supernovae? They rigorously cross-checked every measurement, reanalyzed every data point, and considered every conceivable source of error. The stakes were immense. This was a finding that would rewrite the cosmic story. Yet, the unsettling conclusion held firm. The universe's expansion was accelerating. The independent verification by two competing teams, working with different telescopes and slightly different methods, lent immense credibility to this truly paradigm-shifting discovery. Their reluctant yet undeniable findings forced cosmologists to confront a radical new reality. Something mysterious, something unseen, was actively pushing the fabric of space-time apart, overcoming the universal pull of gravity. It was a discovery so profound, so unexpected, that it earned Saul Perlmutter, Brian Schmidt, and Adam Rees the 2011 Nobel Prize in Physics, awarded for finding something that no one had even been looking for, fundamentally changing our perception of the universe's ultimate destiny. The universe, we now know, is expanding at an ever-increasing rate, its very fabric stretching, pushing galaxies apart with an unseen force. This revelation, born from the meticulous study of distant supernovae, presented cosmologists with a profound enigma. What could possibly be causing this cosmic acceleration? The answer, startlingly, might not reside in the vast, swirling galaxies light-years away, but in the most minuscule, seemingly empty spaces right here on Earth, in a phenomenon so subtle it was once dismissed as a mere theoretical curiosity. Consider a realm where nothing truly exists. Not the vacuum of space between stars, which is teeming with photons and cosmic rays, but a space so utterly devoid of matter, of light, of any conventional energy, that it defines true emptiness. Yet, even in this perfect void, physics tells us that nothingness is not truly empty. It is a roiling, seething ocean of activity, a quantum foam where particles and antiparticles constantly pop into and out of existence, only to annihilate each other in fractions of a second. These are virtual particles, and their fleeting presence, though undetectable directly, has profound, measurable effects. Now, place two perfectly uncharged, electrically neutral metallic plates incredibly close together in this theoretical vacuum, closer than a human hair is thick, perhaps separated by mere nanometers. What happens? Intuition might suggest nothing. There is no air to push them, no charge to attract or repel. Yet, a strange, invisible force emerges, subtly but undeniably pushing these two plates together. This is the Casimir effect, a physical force first predicted in 1948 by the brilliant Dutch physicist Hendrik Casimir. To grasp why this occurs, consider the virtual particles of the quantum vacuum as waves. In the vast unrestricted space outside the two plates, waves of all possible wavelengths can spontaneously appear and disappear. But in the tiny gap between the plates, only waves with wavelengths that fit precisely into that microscopic space are allowed to form. It is like trying to play all possible musical notes inside a very small, confined room. Only certain wavelengths, certain notes can resonate. This restriction means there are fewer virtual particles, fewer waves, existing between the plates than there are outside them. This imbalance creates a subtle but persistent pressure difference. The unrestricted quantum activity outside the plates pushes them inwards, while the restricted activity inside offers less resistance. The plates are, in essence, being gently squeezed by the very nothingness of space. For decades, the Casimir effect remained largely a theoretical prediction, too minute, too elusive to measure with precision. But in 1997, a breakthrough experiment by Dr. Steve Lamoureux at the University of Washington finally provided the first precise, undeniable experimental confirmation of this strange, invisible force. Lamoureux's ingenious setup, working at microscopic scales, meticulously measured this tiny inward push between a spherical lens and a flat plate. His results were a resounding validation, proving unequivocally that the quantum vacuum, far from being a tranquil void, is indeed a seething cauldron of virtual energy, a dynamic landscape of creation and annihilation. The implications of this laboratory trick extend far beyond the sub-nanometer scale of two metal plates. Cosmologists, grappling with the universe's accelerating expansion, realized something profound. If empty space itself possesses intrinsic energy, a vacuum energy as demonstrated by the Casimir effect, then this energy would behave in a very specific, astonishing way. It would act precisely like Albert Einstein's long-discarded cosmological constant, that theoretical fudge factor he introduced to keep his universe static, then famously called his greatest mistake. This vacuum energy would exert a negative pressure, an outward push that intrinsically belongs to space itself rather than being caused by matter or radiation. Instead of pulling things together like gravity, it would drive space apart, accelerating the expansion of the cosmos. The observed acceleration of the universe could, therefore, be explained by the subtle, ever-present energy of the quantum vacuum, a property woven into the very fabric of reality. But this seemingly elegant solution quickly spiraled into what is arguably the most profound, most embarrassing problem in all of modern physics: the cosmological constant problem. When theoretical physicists applied the sophisticated tools of quantum field theory to calculate the expected strength of this vacuum energy, the answer they derived was utterly catastrophic. Their calculations predicted a vacuum energy density that was famously 120 orders of magnitude larger than what astronomers actually observe in the accelerating universe. To put that staggering discrepancy into perspective, take a single grain of sand. Now, consider every single grain of sand on every single beach on Earth, then multiply that unimaginable number by itself. Even that would not come close to representing the difference between what theory predicts and what observation reveals. 120 orders of magnitude means the theoretical prediction is a 1 followed by 120 zeros compared to the observational value. It is a difference so vast, so utterly incomprehensible, that it stands as the largest discrepancy between theory and experiment in the entire history of science. This colossal mismatch sends a chilling message to physicists. Our fundamental understanding of reality is deeply flawed. Either our theories of quantum mechanics, which describe the universe at its smallest scales, are incomplete or incorrect when applied to the vastness of the cosmos, or our theory of gravity, Einstein's general relativity, is missing a crucial piece of the puzzle at cosmic scales. Perhaps both are subtly, fundamentally wrong. The quantum vacuum offers the most compelling, yet simultaneously the most problematic explanation for dark energy, a profound embarrassment that hints at a revolution in physics yet to come. The very fabric of our universe is expanding, stretching outwards at an accelerating rate, driven by a force so profound, so elusive, we call it dark energy. For a time, the simplest explanation, a fixed cosmological constant inherent to space itself, seemed to fit the observational evidence. But as we delved deeper, a monumental problem emerged: the quantum vacuum, the nothingness of space, predicted an energy density so astronomically vast, a 1 followed by 120 zeros larger than what we observe, that it shattered our understanding. This staggering discrepancy, the largest in the history of science, forced physicists to confront a chilling possibility. Perhaps dark energy is not a static, unchanging property of the cosmos. What if this cosmic chameleon, this invisible architect of our universe's destiny, is actually changing its mind? The notion of a cosmological constant, while elegantly explaining the accelerating expansion, implied that the energy of empty space was a fixed, unchanging entity, like a foundational law etched into reality. But with the quantum vacuum presenting such an overwhelming theoretical mismatch, scientists were compelled to push beyond this singular idea. In the late 1990s, a new, more dynamic concept began to take hold among theoretical physicists, championed by researchers like Robert Caldwell, Rahul Dev, and Paul Steinhardt. They proposed a hypothetical entity they termed quintessence, borrowing a word from ancient philosophy, referring to the fifth purest element thought to compose celestial bodies. Unlike the static, unwavering nature of a cosmological constant, quintessence is envisioned as a dynamic field, a pervasive energy woven into the universe's tapestry that can subtly shift and evolve over cosmic time and across vast distances. To grasp this, consider a ball slowly, almost imperceptibly, rolling down an incredibly gentle hill. The field's potential energy is what drives the cosmic acceleration, pushing space apart, much like the ball gaining momentum as it descends. However, as the universe ages and expands, the properties of this field, like the slope of our cosmic hill, can change, allowing its influence to wax or wane. This introduces a critical diagnostic tool for cosmologists, a way to measure and characterize dark energy: the equation of state parameter, represented by the letter W. This parameter is a simple yet profound ratio. It compares dark energy's pressure to its energy density. For the cosmological constant, the classic, unchanging idea of vacuum energy, W is always precisely -1. This exact value signifies a constant negative pressure that eternally pushes space apart, never weakening or strengthening. But for quintessence, the situation is far more nuanced. Here, Gu could be a different value, falling anywhere between -1 and -1/3. More importantly, unlike its static cousin, the U value for quintessence could actually change over time as the universe evolves. This subtle variation in U is what future observatories are designed to detect, searching for tiny deviations from -1 that would confirm the dynamic evolving nature of dark energy. Such a discovery would not only rewrite our cosmic history, but offer tantalizing clues about the fundamental forces governing the cosmos. Yet, the scientific imagination, unburdened by current observational limits, dares to explore even more exotic possibilities. Delve deeper, and you encounter the chilling concept of phantom energy, a truly bizarre theoretical substance where the equation of state parameter, W, plunges to a value less than -1. This is where the universe's fate takes a truly terrifying turn. Unlike all known forms of energy, phantom energy would possess the astonishing and counterintuitive property of increasing in density as the universe expands. The more space stretches, the more potent this dark force becomes, creating a runaway acceleration. Such a scenario would culminate in a cataclysmic future event known as the Big Rip. As the universe expands with ever-increasing ferocity, the phantom energy would grow so powerful that its outward push would eventually overcome all other fundamental forces. First, it would tear apart gravitationally bound structures like clusters of galaxies, then individual galaxies themselves. Stars and planets would be ripped from their orbits, their very matter atomized. Finally, at the very last moment of cosmic existence, the accelerating expansion would become so immense that it would overwhelm the strong and weak nuclear forces, tearing apart atoms themselves, reducing all matter to its fundamental, disconnected constituents, leaving behind a truly desolate and infinitely dispersed void. This landscape of competing hypotheses, from the static cosmological constant to the dynamic quintessence and the apocalyptic phantom energy, illustrates that dark energy is not a single, settled idea, but rather a profound cosmic mystery, demanding continuous exploration. For decades, the accelerating expansion of the universe has forced us to confront an invisible, repulsive force, dark energy. We have examined its elusive nature, its proposed forms, from a static cosmological constant to a dynamic quintessence, even the chilling concept of phantom energy. But what if our fundamental premise is flawed? What if dark energy is not a thing at all, not a mysterious fluid filling the cosmos, but something far more profound? Something that redefines reality itself, a symptom of a deeper information-theoretic law governing the very fabric of our existence. To answer this radical question, we must make an unprecedented interdisciplinary leap, bridging the vastness of cosmology with the abstract world of information theory and thermodynamics. This journey begins with a truly mind-bending idea, one that challenges our intuitive understanding of space and reality, the holographic principle. First proposed in the 1990s by the brilliant Dutch Nobel laureate Gerard 't Hooft, and later extensively developed by American physicist Leonard Susskind, this principle suggests that the entire three-dimensional universe, with all its galaxies, stars, and planets, might actually be a projection from a two-dimensional surface, like a colossal cosmic hologram. Consider a television screen. What you perceive as a three-dimensional image, with depth and movement, is fundamentally encoded on a flat, two-dimensional array of pixels. The holographic principle posits that our entire universe could operate on a similar, albeit vastly more complex principle. All the information contained within any given volume of space, every particle, every field, every interaction, can be fully described by a theory that resides on the boundary of that region, the two-dimensional surface enclosing it. This isn't just a mathematical trick. It's a profound connection between gravity, space-time, and information itself, hinting that what we perceive as solid reality might be nothing more than an elaborate cosmic display of fundamental data. This revolutionary concept sets the stage for an even more audacious theory, one that directly challenges our understanding of gravity: emergent gravity. In 2010, the Dutch physicist Erik Verlinde published a groundbreaking and highly speculative theory that proposed gravity is not a fundamental force, in the same way that electromagnetism or the nuclear forces are. Instead, Verlinde argued that gravity is an entropic phenomenon, an emergent consequence of the universe constantly trying to maximize its information content or, to put it another way, trying to maximize its entropy. To grasp this, consider the concept of temperature. While we perceive temperature as a fundamental property of matter, at a deeper level, it is not. Temperature emerges from the collective, chaotic motion of countless individual atoms and molecules. No single atom has a temperature, but their combined dance creates what we experience as heat. Verlinde's theory suggests that gravity arises in a remarkably similar fashion. The universe, in its perpetual quest to arrange its fundamental bits of information in the most disordered, randomized configurations possible, a process inherent to increasing entropy, inadvertently creates the force we perceive as gravity. It's like the universe is constantly shuffling its deck of cosmic cards, and the resulting patterns manifest as the very curvature of space-time. The stunning implication of this emergent gravity framework for the mystery of dark energy is nothing short of transformative. In this radical view, the observed cosmic acceleration, the perplexing outward push that is tearing the universe apart, is not caused by some mysterious energy filling space, some elusive substance we must find. Instead, it is a natural, inevitable consequence of the universe's growing information content. As the universe expands, its capacity to hold information increases, leading to a relentless drive to maximize that information, to expand further. This creates a positive feedback loop. More expansion means more capacity for information, which in turn drives further expansion. This reframes the entire dark energy problem. It suggests that dark energy is not a substance to be found, a phantom field to be detected in an observatory. Rather, it is a symptom, a visible effect of a deeper, information-theoretic law that governs the very fabric of reality. It's akin to observing the shadow of an unseen dancer and trying to define the dancer by the shadow alone. Dark energy, in this context, becomes the shadow of the universe's fundamental drive towards greater information and entropy, the cosmic consequence of a system constantly trying to spread its data as widely as possible. It is a concept that turns our understanding of the universe inside out, suggesting that perhaps the greatest mystery of the cosmos lies not in what it contains, but in how it processes information. For decades, humanity has peered into the cosmic abyss, confronting a profound riddle. The universe is not merely expanding, but accelerating, driven by an unknown force we call dark energy. While theoretical physicists propose astonishing, even radical, explanations, from the subtle hum of the quantum vacuum to the very information content of reality, the ultimate truth can only be found through observation. The questions are vast, but the answers must be precise. This relentless pursuit brings us back to the present day, to a monumental global effort, a new era of cosmic cartography where the stakes are nothing less than the destiny of everything. At the forefront of this grand endeavor stands a trinity of next-generation observatories, each a testament to human ingenuity, designed to map the universe with unprecedented detail and finally unmask dark energy. First, high in the mountains of Chile, on the El Peñón Peak, the Vera C. Rubin Observatory is poised to redefine our understanding of the dynamic night sky. Unlike any telescope before it, Rubin boasts an astonishingly wide field of view, capable of capturing an area of sky 7 times the diameter of the full moon in a single image. To put this in perspective, it is like being able to photograph an entire football field with a single click of a camera, rather than painstakingly piecing together hundreds of individual shots. This colossal instrument is set to embark on the Legacy Survey of Space and Time, or LSST, a 10-year mission that will systematically map the entire southern sky every few nights. Imagine creating a cosmic time-lapse video of billions of galaxies, charting their movements, their births, and their deaths. The sheer volume of data will be staggering, equivalent to processing tens of thousands of television shows simultaneously. This rapid, comprehensive survey will allow scientists to discover millions of new supernovae, those celestial standard candles that first revealed the universe's acceleration. By meticulously tracking these explosions across vast distances and over time, Rubin will provide unparalleled precision in charting the growth of cosmic structures, revealing how dark energy influences the very largest formations in the universe. Taking our gaze beyond Earth's atmosphere, we turn to the European Space Agency's Euclid Space Telescope, a marvel of engineering launched in 2023. From its vantage point, 1.5 million kilometers from Earth, Euclid is designed to craft the largest and most accurate three-dimensional map of the universe ever conceived. Its mission, to observe billions of galaxies, stretching back through cosmic time to when the universe was less than half its current age, peering out to 10 billion light-years away. This is not merely a collection of pretty pictures. It is a meticulous measurement of the cosmic web itself. Euclid employs 2 primary methods in its quest. First, it measures the subtle distortions in galaxy shapes caused by what is known as weak gravitational lensing. Think of the universe as a vast, lumpy sheet. Massive objects like galaxies and dark matter clumps subtly warp this sheet, bending the light from more distant galaxies as it travels towards us. These distortions, though tiny, act as cosmic magnifying glasses, allowing Euclid to infer the distribution of both visible matter and elusive dark matter across the cosmos. Second, Euclid charts the distribution of galaxies to detect the faint imprint of baryon acoustic oscillations, or BAO. These are essentially ancient sound waves that rippled through the early universe, leaving behind a characteristic pattern in the arrangement of galaxies today. Because the scale of these ripples is known, a cosmic standard ruler left over from the Big Bang, mapping their distribution allows scientists to precisely measure the expansion history of the universe. Finally, we look to NASA's Nancy Grace Roman Space Telescope, set to launch later this decade. Roman promises to be a true powerhouse, offering a field of view 100 times wider than that of the venerable Hubble Space Telescope. If Hubble is like looking through a straw, Roman is like peering through a massive panoramic window. This enormous field of view is critical because it allows the telescope to perform multiple types of dark energy surveys simultaneously, observing vast cosmic volumes in a single glance. It will use both supernovae and gravitational lensing, as well as new techniques, to independently confirm and refine the measurements made by Euclid and Rubin. This trio of observatories marks a fundamental shift in humanity's approach to the cosmos. Gone are the days of single, serendipitous discoveries, though those remain vital. We are entering an era of precision cosmology, where the goal is no longer just to detect dark energy, but to measure its properties with exquisite accuracy. Specifically, these missions are meticulously designed to pin down the equation of state parameter, W, that critical number that defines dark energy's behavior. For a cosmological constant, that original, unchanging idea, W, is exactly -1. But if these next-generation telescopes detect even a tiny deviation from -1, or if U appears to change over cosmic time, it would definitively point towards a more dynamic form of dark energy, like quintessence. And should they ever find U to be less than -1, the chilling specter of phantom energy and the Big Rip would loom large. This new age of cosmic cartography promises to chart not just the galaxies, but the very nature of the universe's most profound and perhaps most terrifying secret. For decades, the accelerating expansion of the cosmos has been described with a sense of cosmic dread, an unseen force tearing the universe apart. But what if this perception is fundamentally mistaken? What if this mysterious push is not a malevolent destroyer, but rather a profound, intrinsic property woven into the very fabric of space-time, a kind of fundamental cosmic DNA that has shaped the universe since its infancy and will ultimately dictate its distant, final fate? This reinterpretation shifts our understanding from a battle against an alien force to a deeper appreciation of reality itself, a reality where emptiness is alive with purpose. This journey of understanding has been a winding path, paved with unexpected discoveries and profound scientific humility. Consider the faint, persistent hiss that baffled two radio astronomers in 1964, a background noise that initially seemed like a mundane technical glitch, but proved to be the afterglow of creation itself. This unexpected signal, the cosmic microwave background, was the first subtle hint that the emptiness of space was far from passive. It vibrated with the remnants of the universe's earliest moments. Then there was Albert Einstein's discarded cosmological constant, a mathematical term he introduced and later famously regretted, yet one that, in hindsight, perfectly described an inherent outward push of space, a concept he dismissed as his biggest blunder, only for it to resurface as a cornerstone of modern cosmology. The painstaking observations of distant Type 1a supernovae in the 1990s, celestial explosions of such consistent peak brightness that they served as cosmic yardsticks, then unequivocally revealed that the universe's expansion was not slowing, but accelerating. These cosmic beacons, millions of light-years away, appeared fainter than expected, a clear sign that the fabric of space-time was stretching faster and faster over time. And finally, the strange, subtle pressure of the quantum vacuum, a force demonstrated in laboratory experiments where perfectly neutral metal plates, separated by mere nanometers, are pushed together by the inherent energy of empty space, offered a profound, albeit problematic, theoretical explanation for this cosmic acceleration. Each of these pivotal moments, seemingly disparate, points to the same stunning conclusion. The void is not a passive canvas upon which cosmic drama unfolds, but an active, dynamic player in the grand narrative of existence. This cumulative evidence fundamentally reshapes humanity's place in the cosmos. For centuries, our understanding of the universe's ultimate destiny was dominated by the familiar, comforting pull of matter and gravity. We envisioned a universe expanding, slowing, perhaps even contracting back into a fiery, big crunch. But the discovery of dark energy shattered that narrative. We now live in a universe whose destiny is not governed solely by the familiar gravitational embrace of galaxies and stars, but by the mysterious, relentless push of the vacuum itself. It is a universe where the ultimate fate of all matter, all structures, all life, may be dictated by a property of empty space, a force that expands faster the more space it has to work with. This profound shift from a gravitational pull to a vacuum's push forces us to confront the true nature of reality. Dark energy, whatever its ultimate form, whether a constant energy of space, a dynamic evolving field, or something even more exotic like a manifestation of information itself, reveals a universe far more intricate and enigmatic than previously conceived. It suggests that the laws governing reality extend beyond what we can see and touch, delving into the very essence of existence. We are only at the very beginning of this investigation, akin to ancient mariners first charting an uncharted ocean, recognizing the immense scale of the journey ahead. The quest to understand dark energy transcends the boundaries of cosmology. It is a fundamental inquiry into the ultimate laws of physics that define reality itself. It demands a blend of rigorous observation, audacious theoretical speculation, and boundless curiosity. This journey, full of intellectual humility in the face of such a colossal mystery, is perhaps the grandest scientific adventure our species has ever undertaken, a relentless pursuit of knowledge that promises to redefine our place in the cosmic story.